We'll be stopping at 2. Wherever we get, we're stopping at 2 to get ready for your chemical test mini assessment. You'll have the last 15 minutes of class to do that. All right, here we go. Unit 7, Part 1, Intro to Equilibrium. So what is that? What's this? In previous chemistry, you would have heard this called reversible reaction. It's been mentioned in passing here and there, but we haven't really went into detail about reversible reactions. What's a reversible reaction? Reactants turn into products, but then products can connect back with each other to form reactants. Some chemical reactions have equilibrium. It's not just reactants go to products and stay products. They go back and forth, and you can alter the conditions of the reaction to make a better yield of product or to not make a better yield of product. And that's what an industrial chemist might do. And we'll see that in examples in a little bit, where you can change pressure conditions or you can change temperature conditions to force more products to be made. And so the idea of equilibrium is that these are reversible reactions. Here, reversible reactions look like this. So from now on, if you see a reaction that looks like this, reactants go to products, just one arrow, that means the reaction's not reversible. Once your products are made, that's it. As long as conditions remain the same, your products cannot be changed to reactants. And so that's just a brief idea of what's going on. You're going to learn a very, very, very important concept in chemistry today that you probably have never heard of before. It's called Le Chatelier's principle, and it is one of the most important ideas of equilibrium. So, give a little bit of time, and then we're going to get into it. Julio, did you understand the explanation here?
Yeah.
So this basically is your raw score of your average cup 6. You add 15% to that for the before it goes in. Because every time you're in the top half, it's so 3 times 5. Yeah, go ahead. The pass here, so yes, you got it. All right, continue. Good. All right, here's our objectives. It looks like a lot, but it's not as much as it looks. But I do need you to focus and pay attention. First thing, understand what is meant by the term reversible reaction. Second, understand what is meant by dynamic equilibrium. So these are definition type things. The rate of the forward reaction and reverse reactions are equal to each other, and the concentration of reactants and products remains constant. Understand the need for a closed system. You may want to underline those 2 words. A closed system in order to establish dynamic equilibrium. Then after we go through our intro explanations of what is even happening here, we're going to look at Le Chatelier's principle. Whenever you have a definition, you may want to get in good practice because we're starting to revise. Like we're in the final unit. We're in the last 10% of what we got to cover in this class. You may want to start putting this stuff on flashcards. If something says define, that means if Cambridge asked for it on a test, they want word for word the definition it says in the standard. So define Le Chatelier's principle as this specifically. If a change is made to a system at dynamic equilibrium, the position of the equilibrium moves to minimize the change. So this is like a word for word definition. I'll explain what exactly this means as we go through. But I'm just saying, if it says define, if that's your command from Cambridge, that means when they test it, they're looking for word, whatever it says afterwards. And so you'll want to go back through the standards and the syllabus and make sure you capture all those defines, maybe in flashcards or like in a Quizlet. I know Kat shared one from Ramsey's that he made last year of all the different definitions that you could go study for the day. All right. Use Le Chatelier's principle to deduce qualitatively from appropriate information the effects of changes in temperature, concentration, pressure, and a catalyst on a system at equilibrium. So if we change the pressure, how does that change the direction of the chemical reaction? If we change the concentration of our reactants or products, how does that change the direction of the chemical reaction? So on and so forth. And then here is, we're starting to get to the math. Okay, one has bigger than the other, but ignore that. You're not really going to get to the heavy equilibrium math until we come back from break. You're going to start to look at what the math looks like, but today will be, make sure you're focusing on me. Today will be almost exclusively theory, very little math. The math will be when we come back from spring break, the lessons when we come back from spring break. So there will be homework given today, sorry. There will be homework given today. That homework won't be due until the end of spring break. It'll be just one of those regular written homeworks. So if you get it done and you understand this topic and you can do it quickly, do that. If you'd rather do it before you return for the next lesson to be like, hey, what did we do again a week and a half ago? Do it that way, whatever works best for you. Can this show up on the quarterly? Yes. I'm going to be clear. Today's lesson can show up on the quarterly. All right, but not the test on Thursday, to be clear. Okay, so here we go. I've already brought this up. Reversible reactions, you're always going to see them as double arrows. This is the formatting from Microsoft PowerPoint, but how you'll actually see it is looking like this. A half arrow and then a half arrow going the other way, typically. And this represents equilibrium, meaning some products are left at the end of the reaction, but also some reactants. Now I'm saying the word some, but we're actually going to learn exact amounts. We're going to learn the quantities later in a different lesson. Irreversible reactions means that every reactant turns into product. And at the end of the reaction, there are no reactants left and everything is a product. And that's the definition for dynamic equilibrium. Yes? Prepare it's pretty much a full paper. Your quarterly, to be clear, will be a full paper 2, specifically, for quarterly group. And it will be graded on a Cambridge grading curve. But no multiple choice on quarterly group. That's how I always do it. So you can mentally prepare yourself for that. A few weeks from now. It's April 4th is your quarterly. April 4th. But not the first day we come back, the second. All right, anyway, dynamic equilibrium. This is when the rate of the forward reaction and the rate of the reverse reaction are the same. And this means we have reached equilibrium. So what you'll see here is a reaction going forward. What that means is that you're forming products at a greater rate than you're forming reactants. So products are formed at a greater rate. Just to explain, what does that mean? Big arrow going towards products. Reaction going backward. We also say the reaction's shifting towards reactants. This means that reactants are being formed at a greater than rate of products. Please knock on the door. Thank you. Okay, and then when we've reached dynamic equilibrium, this means the rate of forming reactants is equal to the rate of forming. Yes.
Just me, Julio Rosario's going home.
Okay. Have a great day, Julio. Did you get the homework?
Yeah, you can.
Okay. Just making sure. All right. So a reaction in dynamic equilibrium means the rate of forming your reactants and the rate of forming your products are the same as each other. Make sure you're taking the notes. So what this means is that the amount of your reactants and products are constant at that point. What does constant mean? The amount of your reactants and the amount of your products no longer changes anymore. It's just whatever it is, that's what it is. That's what it's settled out to be. So at equilibrium, you'll have a constant amount of reactants and a constant amount of products. So that's important to know. So you're going to see a bunch of features about dynamic equilibrium on the next slide. They are actually all important to be aware of. I'm gonna give you about 20 more seconds to write down what I had here. Products formed at a greater rate. If I say the reaction's going backwards or going to the left, that means the reactions are being formed at a greater rate. And if I say that we're in equilibrium, the rates are the same as each other. Yes. Go ahead. Yes. Or whatever the Thursday is. The Thursday we come back. Whichever day. You can take it early if you want. Or you can take it as long as you take it by the 9th. That's when the quarter ends. Yes.
So they're only at equilibrium if they're at constant.
A constant rate. And the rate no longer changes. And so we're going to discuss how do we change the rate.
Does that mean everything, like,
Every
either
chemical,
going forward or backward is constant?
that's not an equilibrium. That's not irreversible. Most reactions, like once they've settled, are at equilibrium. They're reversible. But we can change conditions to make them no longer at dynamic equilibrium.
So if it's irreversible,
Then you don't have this. If it's irreversible, done.
That just means there shouldn't be.
There's no reactant. There's no way to shift it. There's nothing you can do to the temperature. There's nothing you can do to the pressure to get reactants. That reaction only goes to products. Does that make sense? So these features are only of reactions that are reversible. Yes.
So like, just like in the bow, it does say we have the
Higher yield.
same process.
This is going to go into that idea of yield. Sure. All right. So these factors you need to know. First one I've already mentioned. Equilibrium is dynamic. This actually means that word dynamic means constantly, never stops. Dynamic means never stops. Continuously is another word. Continuously taking place. So what this means is that products and reactants are constantly being reformed. Reactants are colliding into each other to form products. Products are colliding into each other to form reactants. And this just keeps happening again and again and again and again forever and ever and ever. That's what dynamic means. The forward and backwards reactions occur at the same rate. What do we mean by rate? We mean the actual rate of the chemical reaction. How fast this reaction is going is the same as how fast this reaction is going. So how quickly that happens. The next thing that's important is that the concentration, molarities, the word that strikes fear, the molarities, or the moles DM minus 3 of the reactants and products stay the same at equilibrium, meaning that at equilibrium you've got a final concentration of each reactant and you've got a final concentration of each product, and it will stay the same. Yes. Yep. I'm just going to write that out here. Mole DM minus 3 equal molarity equal concentration. The only concentration unit that Cambridge uses is molarity, so we're going to say yes, yes to that. There are other concentration units that exist, but we're not doing that. For the purposes of this course, in a further study of chemistry, you would see there are other concentration units, but for the purposes of our conversation here, we only use molarity. Any change in concentrations from equilibrium amounts. So if we change the amount from the amount that we had at equilibrium, like we have more reactant, we'd be like, let's add more reactant. That will cause a shift in the reaction. Finally, equilibrium requires a closed system. It's exactly what you think it means. Put a lid on it, right? A closed system means that none of your reactants or products, I like the word escape, they can't escape. So if you put a lid on it, or a stopper, right, it will hold gases. And even liquids evaporate. Do you agree? If If you have like a bunch of water, will it eventually evaporate over time? So how do we stop that from escaping? Add a lid. That's why your bottled water never changes volume, because it's got a stopper on it. But if we were to just leave out a beaker of water here, I mean, we could do that for fun before spring break. Leave out a beaker of water and put the volume that it would be poor. What?
I have so many gripes with bottled water taps. They don't work. They never work. Like for the disposable ones, they do not work.
Not well. Maybe not a completely closed system. All right, and then an open system is like our regular reactions. If we just have a beaker and it's open to the environment, then your reactants or your products can escape. So what does equilibrium require? To form equilibrium, you need a closed system. So there has to be a lid on the container in order to have a specific amount of reactants and products. So in industry, they keep everything like in these big metal tins that are closed. All right, so let's continue. Changing the position of equilibrium. So this is what a chemist might do. What if I want to make more products? So what if we need to force a reaction at equilibrium to make more product or more reactant? Like, let's say it's the reactant you needed. What would you do?
More catalyst?
Catalyst will get to the same place faster, but it won't make more. It goes to the same place, like you get the same final amount, it'll just get there. So you can change the concentration of one of your reactants or one of your products. You could change the temperature of the reaction. You could change the pressure in the reaction. You could actually even change the volume in the reaction. And so if we are trying to change the position of equilibrium, like do we get more products or do we get more reactants off of the standard dynamic equilibrium, we can alter the reaction conditions in such a way to force the reaction to be shifted either towards products or towards reactants for a limited period of time until equilibrium is reestablished. And so this is referred to as Le Chatelier's principle. It's very important that you know this. And Le Chatelier's principle, the formal definition is on the first slide, but the main idea of it is the following. It has to do with stress, and I think we can relate to that. I think all of us can relate a little bit to stress. When a system has stress added to it, what do you think the system does? What do you do if a lot of stress is added to you?
Collapses?
Are there any other things that could happen?
Burnout?
Burnout. Great. Oh boy. Whenever I do this in Cambridge classes, I'm like, I know y'all are very stressed. The extra stressful time of year, testing around the corner. What happens is the system will work to reduce the stress. And so what could that mean, like, psychologically? That could mean that we got a test coming up and we run away from it. And we stay home instead of coming to school. Not realizing that, I still have to take it. But I've eliminated the stress for a little while. It could mean that, you work very hard and you eliminate the stress by getting it done, right? It's like, system will work in whatever way it can to reduce the stress that has been applied. And so the way that Chambers says is that it will operate in a way to minimize the stress. So the way to understand it is if you force too many reactants in a dynamic equilibrium, what do you think is going to happen? The stress added is to the reactant side. You add more reactants. What do you think is going to happen? to shift from reactants to products. That's how the Chatelier's principle works. Whatever side has too much added to it, the system will work to make the opposite to reestablish balance. So you can think of equilibrium as balance, actually.
And it works by probabilities.
And it works, yeah, just going back and forth. And so, does that idea, at least at its outset, make sense? So system works if extra stress is added to minimize that stress. And the way it's going to do that is by shifting equilibrium to the opposite direction of where the stress was applied. So basically running away. You can even psychologically minimize the stress. All right. What are factors that affect equilibrium specifically, the ones that you need to know? You can change one of three things to alter equilibrium. The first thing you can change is concentration. That means you can make, that really is just, do I have more reactants or do I have more products? So this is either add more products, add more reactants, or less. Alter the concentration. So either more or less reactants or products. This will shift equilibrium in a desired direction. We can change the pressure. What does that mean when we change the pressure? What are we doing by changing the pressure of the system? What is pressure? If we increase pressure, what does that mean we're doing?
And that's one thing there.
We're pushing the molecules closer to each other, right? So increasing pressure, remember pressure is defined, if you want to know this, is force divided by area. That's what pressure is. So if I increase the pressure, it means I'm increasing the amount of force, the amount of molecules sitting in the wall of the container over a given area of space. So we can do that by changing certain things.
So it can either be increased force or increased area, right?
Right, exactly. Which means the volume also could be affected, right? So if pressure has an effect, does that also mean volume has an effect?
Yes.
Because if you're changing the area, you're changing the range. That actually means pressure and volume changes in effect. And the idea is pressure up means volume down. They're inversely proportional to each other. If I decrease the volume, that's what I was showing here, right? Decrease the volume is actually increasing the pressure. Think of constricting it. All right, temperature. This is the hardest one to analyze because it actually matters whether the reaction is endothermic or exothermic, where the stress is applied. And so we are going back to enthalpy today. We're not going to be doing math with it, but we're going to be looking at the concept of enthalpy today. Ready? I'll pause for a little bit. Yes. Go ahead. Chemical test. Not IR. IR and mass spec will be on the unit exam on Thursday. The only thing on today's mini assessment is chemical test.
When they do pressure,
Which will change the volume, will change the pressure. Because if you make it smaller, it means molecules in the volume process. That's the idea. All right, continue. We're good now? All right, so let's see if we can get this idea. This is supposed to be a reversible reaction. You see the double arrows here? And they ask you to explain what happens to the position of equilibrium. So the way you're going to answer this is either the position of equilibrium shifts towards products or it shifts towards reactants. So how you answer. How to answer when that question is asked. Shifts towards reactants or you are also allowed to say shifts to the left. But if you are like me and you're not great, I wasn't when I was your page left and right. I use my hand to tell which one I write with. But you could either say shifts towards reactants or you could say shifts to the left. And the other thing you're allowed to answer is shifts toward products. equilibrium not change? Would we be given something that doesn't change the position of equilibrium? Or no change? Those are really your options. This does not affect equilibrium. All right, more CH3, COO, C2H5. Hey, we know what that is, but we just have to match it here. If I add more product, what does the system do?
It shifts to the left reactant.
Correct. So the idea is you have to analyze which side is more stress being added to. More stress is being added to the product. So the system does the opposite. If more stress is added to the products, the system will restore balance by adding more to the reactant. So basically connecting these two and making more reactant. And so the answer to our question is shifts toward reactant. And are you also allowed to say shifts to the left instead? Yes. What about the next? So C2H5OH is removed.
Oh, it shifts to the right. Shifts toward carbon.
But removed, not added.
But it's
This is a reactant. Isn't this saying that there's less stress on reactants?
oh, okay. So
Less
it goes to the
stress
reactant.
on reactants.
Moves to the reactant.
So there's too little stress now. And less stress on the reactants is AKA saying what about the products? That there's actually more stress on the products side. So what happens to the position of equilibrium?
Moves toward the reactant.
Correct. Shifts again towards the reaction. So if I take away something from the reactant side, if I have less of it, it'll actually shift towards that side, whatever I have the less of. Shift towards reactants to restore balance. So what have we learned so far? If we increase one side of the reaction will go to the opposite. And if we decrease a side of a reaction, it'll actually go to that side to bring it back to even. Yes. It's going to work to make the same amount of stress on the other side to restore balance. So it's going to decrease its stress by increasing the stress on the other side to restore balance. So whatever I have too much of, it shifts to the other side. But if I have too little of something, the other side goes to the other. That's the idea. It goes back to even, no matter what. The whole idea is it's got to end up equal at the end. You reach equilibrium. So it equalizes. That's the way to think of it. To go back to dynamic equilibrium. So, let's take a look at this one. What happens to the position of equilibrium when I increase the concentration of Fe2+? So we got this one? So I'm increasing stress on my reactant, right? Increasing stress on reactant. So what does the reaction do as a result? Shifts to the right, which is shifts to the product, right? I'm gonna write shifts towards products, but you can feel free to write shifts towards the right. I like that second question. Water is added to the equilibrium. So it'd be diluted, right? But this is aqueous.
Oh.
This is aqueous.
All it would be constant.
So you dilute everything. So you're diluting everything by the same factor, right?
So
So
no reaction.
No change. Yeah. Then it would matter. So like if this was solid and you had two aqueuses over here and one aqueous over there, then you've got more water on this side, right? So then it would be diluted. This would lower the concentration and it would go that way. So it has to do with dilution. Dilution lowering the concentration. However, the concentration here is lowered for everything. Dilution means lower concentration, but everything is diluted equally here. So that's why no change. Hey, was there one other thing that I maybe mentioned at some point doesn't change equilibrium?
Water.
water's mentioned here. What's the other thing that doesn't change the position of equilibrium? It was brought up, and I said, hey, this doesn't. It gets there faster, but it gets to the same place, right? So catalyst also doesn't change position of equilibrium. You want to write that note for yourself? Because they could trap you with that on a paper 1 question.
Oh, the paper one question could ask that?
Sure. It'd be like, what shifts the equilibrium this way? And they put like a catalyst, H3PO4, like, and then you just have to know, not that one, something else. Yes? All right, we got a couple more here before we continue. You're going to see next, we're going to talk about the effect of pressure and the effect of temperature. Pressure is easier to analyze than temperature. I would say that concentration is the easiest to analyze. So we did that one first. I always like to do the easiest thing and then ascend in difficulty as we go along. So, pressure. Technically, pressure changes should really only matter for gases. Why? Liquid is a condensed phase. So when we're talking about effects of pressure, this should really only be looking at the moles of gas,
Right, because it's spread over here.
because that's spread over an area, whereas liquid is a condensed phase. No matter if you put liquid in a gigantic container, yeah, the liquid's gonna fill the bottom of the space, but whether you have a container that's that big or that big, it's not gonna change your liquid volume at all. Whereas if you have a gas container, we know that gases actually fill the container that they're in. They fill all the space they have available. So if we increase the volume, we decrease the pressure, actually. And so it's important to note, and I wrote this as review from when we studied gases, it's important to note that the more times we have molecules hit the wall of whatever container we have, the more pressure we have. So what you're going to be analyzing here in an increase in pressure is you're going to be looking for the side of the reaction that has the most gas, because that's the side that's going to be affected by an increase in pressure. So let's see what that means. Let's take a look at it. Predict the effect of increasing the pressure on each of the following reactions. So the way you need to read it is you compare the moles of gas. The left side of the first reaction has how many moles of gas? So that's how you interpret it. 1 mole gas. It doesn't matter what the identity of the gas is, it's just gas. How many moles of gas are on the product side? 2 moles gas. So which side itself exhibits more pressure? The right side. So here's what I want you to do, and this is how it was taught to me when I was studying chemistry. You write the letter P on the side of the reaction where there's the most moles of gas, treating it as if it was a reactant or a product. So when you increase or you decrease, you know which side you now have added stress to or have decreased stress on. So we add pressure to the side of gas, to the side of the reaction, to the side of reaction that has most moles of. Are you okay with me writing RXN? When you go to college, shorthand writing is helpful because you learn stuff like really quickly. My organic professor spoke about 500 words per minute. So y'all think I'm really fast, but I'm not. That's why I had to record. I don't know if I told you I recorded her lessons because that was the only way I could maintain the name in the class. Because otherwise, I'm not an auditory learner. I needed to go back over it again. Back then. I feel old. No, we actually bought like 4 recorders, and then we asked permission and it was only audio. Like no visual. Yeah, we didn't have that. All right, ready? So, knowing that I'm increasing the pressure in this first reaction, which direction does equilibrium shift?
Left.
Correct. Because the way to understand it, there's more pressure on the right side, so I'm increasing stress on the right side. When I increase pressure, I increase stress on the side that has the most pressure. I'm increasing that at a greater rate. So I'm increasing stress on the product side. And Le Chatelier's principle says the reaction is going to work to minimize that stress. Too much stress here means make more there, which make more reactant, which means shift toward reactants or shift to the left. Let's take a look at the other one. Calcium carbonate. Hey, do you remember what type of reaction this is?
Decomposition.
What specific type of decomposition?
Oh, thermal?
Thermal. Could that be on your board, really? Sure, Ken. We learned that. Thermal
No,
decom. Thermal decom. You start with a solid and you break it down and release some gas. So, how many moles of gas are on your reactant side here?
1.
Is calcium carbonate a gas?
No.
So, how many moles of gas? Yes.
0.
Okay, go ahead and get it.
0.
0 moles of gas. So you should write that. It's 0, right? You have no gas. So no matter how you change the pressure, nothing, like, no gas here. 0 gas. 0 moles of gas. On the product side, how many moles of gas? Product.
Oh, that is a simple.
How many total moles of gas do you have on the product side?
1 mole.
Right? Now you compare reactants versus products. Which side has more gas?
Products.
So you put the invisible.
That'd be.
I put like quotation marks around it because it's not the element phosphorus. I don't want you to think it's that. It's just like if pressure was on the side, it would be on this side. That's the way to analyze it. And so praseodymium is PR. Right? Anyway, what do we do now?
Shift
We're-
to the left.
Because this again, we're increasing stress on the product side, so the reaction is the opposite by making more reactants. Shift towards reactants. So we have now looked at the effect of changing the concentration. We could change the concentration of a reactant or a product to change the direction of equilibrium. We know we can change the pressure if we've got gases. We can change the pressure to change the shift in equilibrium. And so the last thing to analyze is going to be the temperature. And like I said, this one's the most complicated to recognize. So let's take a look at this one last one before we get there though. Predict the effect of decreasing the pressure. You should always underline your key here. That's what it's asking for. What's the first thing to do though?
Count the moles of gas on each side.
And the sides we mean are these sides, right?
Yeah.
Okay, you got it?
So the right side has more
Moles of gas.
moles of gas in it. So oxygen counts as one.
Okay, so I'm writing that out. On my reactant side, I've got 2 moles of gas. Do you agree? On my product side, I've got 3 moles. Agree with that? It don't matter what the identities of the gases are, it's just how many gases we have that are filling that container. It's really this idea of knowing that 1 mole of any gas fills the same amount of space. And so, so pressure goes on the product side, right? Because that's where the most moles of gas are. So this question says we are actually decreasing the pressure, which means less stress on the product side. So what does that mean? What is the reaction going to do? Less stress on the product side. So in order to restore balance, if you've got too little on one side, what is the reaction going to do? To restore balance, it's going to shift to the right. That's correct. Shift towards product. whichever side has less stress, that's the side the reaction will shift to restore equilibrium. Shift towards product. There are 3 moles of gas on the product side. That's the side where pressure is on. So if you decrease the pressure, you're decreasing the pressure more on this side versus that side. And the last one, pressure was on the product side because you had 1 mole of gas versus 0. Every example you've seen, the most moles of gas have been on the product side. That doesn't mean that it will always be on the product side, but that's just every example we've seen. 1 versus 2, 0 versus 1, 2 versus 3. Yes? Question? On what? Enthalpy? Enthalpy?
I don't understand why.
Oh, no, we're not there yet.
Here it's decreasing on the other one, it's increasing.
Instructions were different.
Oh.
Instructions are different. You got to pay careful attention to what it's asking. Remember, the whole idea of the Chatelier's principle is to restore balance. So if there's too much on one side, you go to the opposite. If there's too little on one side, you go to that side. Does that make sense? Okay. So, last on Le Chatelier's principle is the effect of temperature. This is the most difficult one to remember, but I am sure you can do it. It depends on whether the reaction is endothermic or exothermic, how temperature is going to affect your reaction. So that means you're going to have to be able to look at something called delta H in question. Remember that thing? What happens if enthalpy is positive? The number is positive. I don't care what the number is. Positive 120, positive 2, positive 10,000. It means that it's endothermic. And what does that mean to us? Like, what is at the very basic? What does that mean?
Like we're absorbing heat from the outside.
It has to absorb energy, right? As a net result of that reaction, energy is going into that reaction. So from reactants to products are going to have more energy than the reactants. Okay, so far so good. And then delta H is negative. What does that mean? Exothermic. And this means that energy is actually being released. And so we use this idea to help us, just like with pressure where we assign the side of the reaction, for temperature we're going to do the same. If we have an endothermic reaction, this means that heat is going in. So we do reactants plus, you can even say energy instead of temperature, right? But I know that how it was taught to me is we just put like a letter T there. So our altering of temperature is going to be on the reactant side because energy is going into that reaction. And then that's going to get us to product. And then for exothermic reactions, you would put temperature on which side of the reaction?
The hard side.
Because energy is released. So we just use the letter T instead of writing the full word temperature. And so you're going to have to analyze reactions, look at the delta H, whether it's negative or positive, and you're going to be responsible for assigning what side of the reaction temperature's on. Ready? Question. What will be the effect then of raising the temperature on this reaction? To be clear, there's a positive here, and you should write a positive there. There should be a sign that says positive. Because remember, for enthalpy, you need to get the sign. So what would be the effect of raising temperature on this reaction? How would you analyze it?
The temperature will
So the first thing is endothermic means absorbing energy. So this means all changes in energy would be taking place in the reactant side because that's what's happening in this reaction is it's absorbing energy as its net result. So how we analyze that is we would write T on which side of the reaction? The reactant side. like it was any reactant or product. We're just gonna add the letter T here. Energy plus hydrogen plus carbon dioxide makes steam and carbon monoxide. Oh, that's a nasty looking reaction. Making carbon monoxide. Sometimes it looks like we just see letters, but I don't see letters. I'm like, I would not want to do this IRL. No, thank you. Somebody brought up something. I don't know if I'll have to tell you over it. But did you know that CO and CN have pretty much the exact chemical structure? Did you know I didn't think that. Carbon monoxide, is that dangerous?
Yes.
Will that kill you?
Yes.
What about CN minus? You know what that is? Cyanide, is that dangerous? Will that kill you? Did you know they have the exact same chemical structure? Carbon monoxide and cyanide? It just hit me when somebody was asking about it in the fourth period because they were asking about like cherry pits. You know cyanide's a cherry pits, right? Yeah, you're not supposed to eat pits of cherries, just heads up. You know the mechanism of action? I mean, if it's a micro amount, you know, you're still here.
Five,
So.
1 day. I was running around and I accidentally.
So anyways, the mechanism of action is that it binds to the hemoglobin in your blood instead of oxygen. And so it will, like, asphyxiate. You press pass out, right? That's the mechanism of action. Anyways, I just was bringing up, like, you guys see, like, just letters sometimes, but it's not just letters. This stuff has meaning. I would not do this reaction IRL. But anyway, in real life. But anyways, positive 41.3, yes.
So we always write the D on the reaction side?
If it's endothermic. If it's exothermic, that's why I said you have to analyze. Endothermic means reactive side. Exothermic means product side. Because it's releasing energy. So then, what's the effect of increasing the temperature? What is the effect?
The equilibrium changes.
How?
It goes.
How do we answer the question?
It goes. It shifts to the right. No.
Position of equilibrium shifts in which direction? Correct.
Okay. Because
Shift
you're adding temperature. to the
towards
reactants.
Product
So you
or
have
to the
to
right?
add energy to the product side. Adding
So increasing the temperature increases the stress on the reactant side. Whatever side you increase the stress to, the reaction works to do the opposite of that stress. So if the stress is applied to the reactant side, the reaction will make the opposite side, which is products, because it can do either way depending on the stress added. So it shifts towards products. Yes? Because it's endothermic. So this was the reason why. Because it's endothermic. It didn't ask me to explain why here, but could you please ask them in Cambridge? Then you'll see when we come back. There's a lot of marks actually, like 4 mark questions on explaining Le Chatelier's principle. Which, if you think about some of the math questions you had some pretty nasty math for 2 marks. Like at the end of the day, the heftier marks are sometimes in your explanations, like understanding ideas. At least. All right. Methanol is manufactured by reacting carbon dioxide and hydrogen. So people, if they want to make methanol, they can actually, and this is actually pretty cool. Think about that. Take some carbon dioxide. Is that available? Take some hydrogen gas. Put them together. You get methanol. And steam. Endothermic or exothermic? So I know this. I'm just prepping my question. All right. What would increase the equilibrium yield of methanol? So what is this question asking? How can I make more methanol? So how can I make more methanol is the simpler way of asking this question. And that really means, how can I alter the conditions to shift the products to, shift towards the, right. So how do I alter conditions?
the reactant. So it's going to be C. Increasing the temperature.
To make more products. This is supposed to say conditions, I just can't write. Conditions. to make more products. Okay. So far, so good? That's just like understanding what's being asked of. So equilibrium yield of methanol means I want to know how do I make more methanol? Adding a catalyst. What is it? Let
That
it
doesn't
show
change
up.
the reaction.
No, it just gets to the same spot faster. Gets to the same place faster. Adding an excess of steam. That means adding to the product. If I add to the product, reaction is going to make me more reactive.
Yep.
That's not what I'm looking for. I'm looking to make more of this. All right, increasing the pressure.
Yes.
Which side of the reaction is pressure on?
The reaction does put the moles
To
of gas.
figure that out, we do 4 moles gas
There's
here,
more moles of gas there.
1 plus 3, 4. Here we've got 2 moles gas, so there's a change. Which side has more gas?
Reactant side.
So we put our little p there. Would increasing the pressure increase the production of methanol?
Yes.
Because increasing the reactants will cause the reaction to shift to make more products. So increasing any stress on the reactant side, basically what's happening is these two are getting pushed closer to each other to make more of this at a greater rate than on that side. Yes?
Why can't you use temperature?
That's a great thing. We'll check temperature. C is the answer. That's been on that for like the past 3 minutes. But I can explain why it's not the temperature. So if temperature is on the product side and we increase the temperature, this means the reaction will shift to make more reactants because the stress has been increased on the product side.
Because it's negative.
So if we're trying to make more methanol, that's actually going to make less methanol. Increasing the temperature will shift the reaction this way. Yes. More moles of gas. So you're looking for the G's and counting the amount of moles to do that analysis. Yes? Yes. If you want to increase the yield of something, like the amount of something, you would increase the opposite side to whatever it is. So if I'm increasing the methanol, if I want the reaction to increase the amount of methanol, I need to alter conditions in such a way where I'm putting more stress on this side. And if I put more stress on this side, it will cause the reaction to make more product. So in this case, more stress on this side would be more pressure. Because this is the side pressure. There's more moles of gas on. So I can, if I was working in industry and I wanted to develop a process to make more methanol, I would increase the pressure in my container, which means smush the molecules closer to each other in some way, add the force or decrease the area. Got it? All right. Uh-oh, the math is here. We got a little bit of time. I want to introduce to you, before we leave out, the idea of an equilibrium expression. And so this will take up a couple of lessons when we come back from break, because it is a hefty topic, but I want you to be aware of what's going to happen. So Le Chatelier's principle, it's big. It's a big topic, but it's a definition topic. So I want you to absorb it, and I wanted to get you through it before break. Equilibrium expressions. So here's the math. We've been saying that in an equilibrium you have some product and you have some reactant, but some is very vague, and you're actually going to be able to figure out how much product versus how much reactant you have in a chemical reaction. And so you're going to have something called, and you want to underline this, K, capital K. Capital letter K, capital K, big K. This is called the equilibrium constant. And even if you end up like, I hate math, I don't want to do math, blah, 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 you have to have understanding of what the equilibrium constant communicates to you. It actually communicates to you the relative amounts of products versus reactants. So for example, if I have an equilibrium constant that says 10,000, And my formula for K, at its very simplest, you don't have to look at all of this yet, but at its very simplest, it's your products over your reactants. If I see the number 10,000, what does that tell me about the relative amounts of my products versus my relative amounts of reactants? This is what KC is.
The product is there's 10,000 times products than reactants.
There's an invisible one here, right? And so what the equilibrium constant will communicate to you is whether there's more products or more reactants at equilibrium in a chemical reaction. So a number like this, that you're absolutely correct, means that there are way more products than less reactants. So just to give you an idea of what that means. Now, you are going to have to develop the formula for the equilibrium expression yourself. And once you get the hang of it, it's actually not crazy. This looks a lot worse than it actually is. So pay attention. You're going to look at your balanced equation. The equation must be balanced. And from your balanced equation, you're going to first look at your products. The equilibrium constant is your products multiplied by each other. So whatever amounts of your concentrations of your products multiplied by each other. So you put a multiplication there, just to remind yourself this is a multiplication. Raised to the exponent of the coefficient. Raised to the exponent of the coefficient of what's in your chemical reaction. So this is going to look a lot simpler when you see examples. And then for your reactants, it's the same idea. Products on the top, reactants on the bottom, always for equilibrium. Hold on to this. So the exponents are your coefficients. Just to be clear, the exponents are your coefficients from your balanced chemical equation in equilibrium expression. I assume that your equations will already be balanced for you. I've always seen them already balanced for you, but if they aren't, then you have to balance them yourself. So let's take a look at what this looks like. There's going to be two different forms of K. And I'll probably have to bring this back up when we get back from break because I'm pretty sure you're going to forget this. Kc is the equilibrium constant for concentration. Kp is the equilibrium constant for gas, which the unit for that is called pascals, actually. I know you're so excited about that. Going back to pascals, too. We haven't seen that since ideal gas law. I don't know. And so there are two formats to write your answer. If you've got Kc, I don't know if you remember this, but I believe I have communicated to you in the past. Whenever we use molarity, you should write it in brackets. And if I haven't, I'm telling you now. Molarity is in brackets. Whenever you have molarity, it's in brackets. When you have gases, you're going to use P and parentheses when you're using gases. So the formatting is a little bit different. And you'll notice when we come back from break that Cambridge is very stingy on your unit. You got to make sure you write it correctly. So write this down. Concentration is brackets. If I'm talking about Kc. If I'm talking about gases, I use parentheses and a letter P in the front to say I'm talking about pressures instead of concentration. They want the notation different. Concentration would be you're in solution. You're doing your reactions like we usually do in solution. And then gases means we're doing gas reactions. Like
Pascals.
And that's Pascals. So before we leave out, like I said, I want to do a couple of these. We're going to do a couple of developing equilibrium expression questions. And if we have time, we'll get to the units. So once you see it in action, hopefully you'll find that it's not crazy. Just remember products over reactants. You multiply, if you have multiple products, you multiply them by each other. And then whatever numbers in the front here in your balanced equation becomes the exponent of your reaction, of your equation. All right, so here we go. Write equilibrium expressions. First of all, for example A, would it be Kc or Kp? Aqueous means you may want to write this for yourself. Aqueous means Kc. Gas means Kp. Right? Concentration is solution, and then gases is peptide. So then we want the expression. So we're going to start this one by writing Kc. What's my first product?
CH3O.
So the idea is you write that in brackets. The identity of this. And what's the exponent of this?
1.
1. There's number 1 there. So this is 1. What is my other product? Do you see another product there? So multiply by concentration of H plus. What is the exponent here? 1. That's it. On the bottom, what is your reactant? How many reactants do you have?
1.
So it's just CH3,
CO.
COOH. So far, so good.
Yes.
So in order to find the equilibrium constant for this reaction, I would take the concentration of this reactant, the concentration of this reactant, multiply them by each other, and then divide by the concentration, or sorry, this product, multiply them by each other, and then divide them by the concentration of the reactants. Remember, it's always product on the top and reactants on the bottom. That's the quick way to remember it. All right, try it again. Second one. Is the second one a Kc or a Kp?
Kp.
So we gotta get used to that format. Kp equals product on the top, reactant on the bottom. So we're gonna do CH3OH. I know it looks a little weird. A little p. P just. And then on the bottom, our first reactant is CO. And our second reactant is H2. What's exponent for that one? Like that. So it matters. If there's a 2 in the front, that actually means that it matters exponentially. It would be whatever that concentration is, it would, or that pressure, it would be squared to find the equilibrium constant. Last one. What do you do now for C? Kp or Kc? Kp. These two come first, so PH2O, what exponent? What's the exponent for this water, H2O gas? 2. And then the other one is Cl2, and the exponent for that is 2. And then on the bottom is HCl, to what exponent? And then the O2. So what exponent? 2. Yes, sir. Like that. So that's how you develop what we call the equilibrium expression, which I would like to call the equilibrium equation. If I were looking at it, yes, Justin, you have a question? That's the standard formatting for pressure. It's not a number. This is just, I will say, notation. It's for communicating that you're talking about pressures here. I'm not a fan of the notation, but Cambridge uses it. No, it would just be brackets. So the notation for concentration is brackets. The notation for pressure is P with a parentheses. So the fact that you've changed, I think it's good enough to change from brackets to parentheses to say that your concentration versus gas, but I've looked at a lot of mark schemes and they always have a little P there. So, yeah. So, be very careful, parentheses versus brackets. Make your brackets look like brackets and your parentheses look like parentheses, because it actually means something different, communication-wise. Brackets, you're saying concentration. Parentheses, you're saying gas.
And when you put concentration, you have to put the C in front of the
You do not.
brackets.
All right, I want to bring up something here. The gas phase contributes to equilibrium. The aqueous phase contributes to equilibrium. These are you have solids or liquids, they do not contribute themselves to equilibrium. The condensed phases of solids and liquids do not contribute to the equilibrium expression. This is actually really important. Instead of writing anything, you just write the number 1 in their place. If you have a solid or a liquid, you multiply by 1 whenever you see a solid or a liquid. So if it was, even if it was like, let's say it was 4 NH3L, it would be 1 to the 4th, which is still 1. So if you have a solid or a liquid, you literally just replace it with the number 1 in the expression. That's important to note before moving on. And that's because only gas and aqueous phases contribute to equilibrium. Movement phases, basically. Oh, like which slide are we on? 19 pages. We gotta be pretty far, is what I'm thinking. So, what affects the equilibrium constant? Pressure changes affect the equilibrium constant. You do not have to know mathematically how they do, but it's important to note that as long as the moles are different, if moles of gas are different, on each side, then it affects the equilibrium. And that's actually how, because it changes the number, it changes the ratio of how many products are made versus how many reactants are made, because it actually changes the constant. It changes the numerical value of the constant. And then temperature. It affects the equilibrium constant the same way by Le Chatelier's principle, and this happens whether the reaction is endothermic or exothermic. So temperature will always affect equilibrium, and it does it by affecting the equilibrium constant, the numerical value. All right, I think we're getting close to where we're going to stop for today. I do want to bring this up because I mentioned this in passing, but I think it's really important you have this concept. If you are to study at the A level, this concept is all over the class, and it's the following. The numerical value of K, I mentioned, it communicates to us the relative amounts of reactants and products. So if you remember whatever K you have, it's always products over reactants. You can look at a number of K and it'll tell you whether this reaction at the end of equilibrium has more products at the end or more reactants at the end. And this is how you analyze it. If K is greater than 1, which we already looked at with the example of 10,000, it means we have more products than reactants. If K is less than 1, this would be saying the following. Let's say we had 0.01. 0.01. What is that the same thing as? Fractionally.
1 over 100.
1 over 100. So understanding that K is products over reactants. If you see the number 0.01, this means for every one product, you have 100 reactants. Does that make sense? So anytime you see a number less than 1, this means that you have a greater amount of reactants versus products. If you see exactly equal to 1, this means the amounts are the same. And if you see a number greater than 1, this means at the end of this equilibrium, you will have more products than reactants. So you could literally just look at the number. I can read this and be like, K equal 2.5 times 10 to the 9th. Oh my God, that's a lot of products. Why did I say it like that? What's 2.5 times 10 to the 9th? 2, 5, and then add how many zeros? Yeah. You left like stuff. It's right under here. I put the hoodie on top of the binder, but you left like a bunch of stuff. You're welcome. Have a good day.
It's actually 2,500,000.
4 billion, right?
Oh,
2,
yeah.
5, and then 8 zeros. That's how I interpret this number. This amount of products versus this amount of reactants. So, at the very minimum, I would like you to be able to read a value of K and have that understanding whether you're making more products at the end of this reaction, more reactants, or if the amounts are the same. We're going to stop here. I think this is a fair spot to stop. Let me just, for the homework, explain real quick. For the homework, because I did not go through the units, any question that mentions units, actually, you know what? come back from spring break because I'm looking. There's about half of it that we haven't done yet. So I'll wait to give it to you till we come back from spring break. Expect though that I'm putting a collisions exercise on equilibrium and the Shetland principle instead to do during spring break because I would like you to visualize what's going on. Collisions you may remember from pre-ACE. There are some like exercises that helps you visually interpret things. I want you to understand the Shetland. You've got 5 minutes to either take a brain break or prepare for your chemical test mini assessment.
That's one. Let's have a question. It's basically like, oh, it doesn't react
Is it gonna be like the most massive for
No. There's no chemical test like that.
all I know is
Yes. And some other reactor. Hold on, this what it is. Come down, come back. Come back here, come back here.
Oh, you're so right. I'm sorry.
why did you do that? I saw it and I like didn't register for a second.
What do you mean liar?
Right, let me go ahead and stop sharing. All right, you've got 4 minutes to brain break or review.